Summary. The minimum energy needed by an electron to come out from the metal surface is known as work function of metal. Energy greater than that of the work function F0 required by the electron emission from the metal surface can be supplied by suitable heating or applying strong electric field or irradiating it by light of suitable frequency. Second, photoelectric effect is the phenomenon of emission of electrons by metal when illuminated by light of suitable frequency. Photoelectric effect involves conversion of light energy into electrical energy. It follows the law of conservation of energy. The photoelectric emission is an instantaneous process and possesses certain special features. Photoelectric current depends on intensity of incident light, potential difference applied between the two electrodes, and nature of emitter material. Fourth, the stopping potential V0 depends on frequency of incident light and nature of emitter material. For a given frequency of incident light, it is dependent on its intensity. The stopping potential is directly related to maximum kinetic energy of electron emitted, that is EV0 equals to half mv square equals to Kmax. Below a certain frequency or threshold frequency mu0, characteristic of material, no photoelectric emission takes place, no matter how long intensity may be. The classical wave theory could not explain main features of photoelectric effect. Einstein explained these features on the basis of photon picture of light. According to this, light is composed of discrete packets of energy called quanta or photons. Each photon carried an energy E equals to h mu and momentum P equals to h upon lambda, which depends on frequency mu of incident light, not on its intensity. Photoelectric emission from the metal surface occurs due to adsorption of photons by the electrons. Seventh, Einstein's photoelectric equation is in accordance with the energy conservation law as applied to photons absorption by electron in the metal. The maximum kinetic energy half m Vmax square is equals to photon energy h mu minus the work function phi naught equals to h mu naught of the target metal, that is half m Vmax square equals to V naught E equals to h mu minus phi naught equals to mu minus mu naught. This photoelectric equation explains all the features of photoelectric effect. Milken's first precise measurement confirmed the Einstein's photoelectric equation and obtained an accurate value of Planck's constant h. This leads to acceptance of particle or photons description value of electromagnetic radiation introduced by Einstein. 8th, radiation has dual nature, wave and particle. The nature of experiment determines whether a wave or a particle description is best suited for understanding the experimental results. Reasoning that radiation and matter should be symmetrical in nature. De Broglie attributed a wave-like character to the material particles. The wave associated with moving material particles is called matter waves or de Broglie waves. The de Broglie wavelength lambda associated with a moving particle is related to its momentum as lambda equals to h upon p. The dualism of matter is inherited in the de Broglie relation, which contains a wave concept and a particle concept p. The de Broglie wavelength is independent of its charge and nature of material. It is significantly measurable of the order of atomic planes spacing in crystal. Only in case of subatomic particles like electrons, protons, etc., due to smallness of these masses and hence momenta, however, it is indeed very small, quite beyond measurement in case of macroscopic objects commonly encountered in the everyday life. 10th, electron diffraction experiment by Davison and Germer and by G.P. Thomson, as well as many later experiments, have verified and confirmed the wave nature of electrons. The de Broglie hypothesis of matter waves supports the Bohr's concept of stationary orbitals.